mixed into asphalt and transformed from waste into modern road surfaces. Behind the black pavement that looks so ordinary lies a complex engineering system. Are you curious how discarded tires can become the foundation of smoother, stronger, and more durable roads? Join Quantivox Tech as we explore the full engineering process behind recycled tire asphalt technology in the US every year. Old car tire overview. The world discards more than 1 billion tires, a figure so vast that when seen from above, many storage sites resemble dark oceans stretching all the way to the horizon. Left in the environment, tires barely break down and continuously release harmful chemicals, turning parts of the United States, Europe, and the Middle East into some of the most severe pollution hotspots on the planet. Yet this massive volume of waste has triggered an unexpected turning point: rubberized asphalt, a multi-billion-dollar industry. Just 1 km of road can reuse up to 10,000 tires while also making the surface more durable, more resistant to cracking, and reducing traffic noise by around 6 decibels. From a symbol of pollution, tires are now emerging as one of the most promising sustainable construction materials of the 21st century. Collection and recycling process of old tires each day. Within the quiet, steady rhythm of modern cities, thousands of vehicle tires reach the end of their service life at roadside garages, maintenance stations, scrap collection yards, and large-scale tire replacement centers. Most of them have already exceeded safe limits for treadwear elasticity and load-bearing capacity. When left in the natural environment, a single tire can persist for decades with little to no decomposition, while slowly leaching organic compounds and heavy metals, becoming a long-term source of contamination for soil and groundwater. In many countries, a worn-out tire is worth only a few cents when sold as scrap. Yet from the perspective of the recycling industry, it represents a true form of urban ore. Inside every tire lies a complex blend of natural rubber, synthetic rubber, reinforcing steel, textile fibers, and chemical additives, materials that can be recovered and reused with significant economic value when processed correctly. The collection process is typically organized along fixed routes. Specialized trucks equipped with high-load platforms and secure fastening systems gather tires from multiple locations to reach optimal transport volumes. This approach not only reduces logistical costs but also prevents tires from being stored outdoors, where they can trap rainwater and become breeding grounds for disease-carrying insects. The recycling process begins with handling the steel reinforcement embedded inside the tire. This component is what allows the tire to lock firmly onto the wheel rim when traveling at high speeds, but in a recycling line, that same steel ring becomes the biggest obstacle if it is not removed first. It can chip cutting blades, snap drive shafts, and bring the entire shredding system to a halt. At the first stage, workers feed the tire into a specialized bead removal machine inside a hydraulic hook system capable of generating enormous pulling force. Digs deep into the tire bead and uses brute mechanical strength to extract the entire steel core in just a few dozen seconds. As you can see, the force is so intense that even the thick rubber body of the tire is violently twisted and deformed during the process. On average, each heavy-duty truck tire like this yields around 2 kilograms of high-quality carbon steel. Once separated, the steel wires are collected manually by workers, compressed into compact bundles, and then transported directly to metallurgical plants, where they begin a completely new life cycle. Meanwhile, the remaining tire carcass is now far more flexible and ready to enter the next stage of coarse shredding. Before mechanical processing begins, the tires pass through a high-pressure washing system that removes mud, oil, residue, and embedded gravel from the surface, protecting cutting blades and crushing shafts from premature wear. This may seem like a minor step, but it plays a decisive role in maintaining the stability and service life of the entire downstream production line. In the primary shredding stage, whole tires are fed into high-torque cutting machines, where slowly rotating alloy steel blades slice them into coarse fragments, measuring several inches across. This low-speed cutting method minimizes heat generation, preventing the rubber from softening or sticking to the blades, while shaping the material into a form suitable for further processing. The shredded pieces then move into secondary grinding, where their size is reduced even further, and the internal steel reinforcement is mechanically fractured and gradually separated from the rubber. High-strength magnetic systems recover the steel directly from the material flow, turning this reinforcement into a valuable stream of recyclable metal. The final output is crumb rubber with tightly controlled particle size, stable enough to move on to classification or reuse. At this stage, the tire has completely lost its original form, and becomes a raw material ready for new applications in construction, transportation, and industrial manufacturing. At the end of the production line, all material passes through a classification screening system. Particles that meet the required size move forward, while larger pieces are routed back to the grinder for further processing. Among these outputs, the fraction ranging from 0.5 to 2 millimeters is especially critical. This is the exact rubber size used to produce rubberized asphalt, which we will explore next. Asphalt production with recycled tires. After crushing and screening, crumb rubber from waste tires still retains residual moisture, fine dust, and traces of impurities embedded within its structure. These factors interfere with how rubber interacts with hot bitumen, preventing the mixture from achieving the bonding strength and stability required for high-performance pavement. For this reason, before it can be blended into asphalt, crumb rubber must undergo a dedicated drying and heating stage to reach the ideal condition for mixing. Inside the plant, the rubber granules are fed into a rotating drying drum, a large steel cylinder, set at a slight incline and kept in constant rotation. Hot air, typically generated by burners fueled with natural gas or fuel oil, is introduced into the drum at temperatures ranging from 200 to 260 degrees Fahrenheit. As the material tumbles inside, moisture is gradually driven off, while the surface of each rubber particle becomes dry and more chemically active, ready to interact with hot bitumen in the next stage. In modern production lines, this process is tightly controlled using temperature sensors and airflow regulation systems to prevent scorching or loss of elasticity in the rubber. Many facilities also rely on indirect heating methods, keeping the rubber isolated from direct flame to preserve the internal polymer structure of each particle. As a result, when the rubber enters the asphalt blending phase, it can swell and absorb bitumen more effectively, forming rubberized asphalt that is more durable, more elastic, and far more resistant to cracking over time. Immediately after drying and preheating, the crumb rubber enters the bitumen blending stage, where the true value of recycling is created. Bitumen is heated separately in storage tanks until it reaches a stable liquid state, typically between 320 and 375 degrees Fahrenheit, ensuring proper flow without degrading its chemical structure. The crumb rubber is then fed into the mixing chamber in carefully controlled doses, with common ratios ranging from 10 to 20% of the total binder mass, depending on the technical requirements of each rubberized asphalt formulation. Inside the mixing unit, heat-resistant paddles generate a continuous vortex, forcing the rubber and bitumen into intense contact for a sustained period of 30 to 60 minutes. During this time, the rubber particles do more than simply disperse. They swell as they absorb lighter oils from the bitumen, a process that increases the viscosity of the mixture, while significantly improving elasticity and crack resistance. These properties are especially critical for road surfaces exposed to heavy traffic loads and constant temperature fluctuations. In modern asphalt plants, the entire process is closely monitored, using viscosity sensors, temperature controls, and residence time management to ensure uniform rubber distribution and prevent clumping. Some systems also introduce stabilizing additives to reduce phase separation during storage or transport. By the end of this stage, the rubberized asphalt reaches a homogeneous and stable state, ready to be used in asphalt concrete production, where discarded tires officially become part of a new generation of resilient road infrastructure. Immediately after the recycled tire-based asphalt mixture is fully blended, it is discharged into specialized dump trucks whose beds have been preheated to prevent sticking or premature cooling. At the time of loading, the temperature is typically maintained between 270 and 300 degrees Fahrenheit, allowing the mixture to retain its workability and self-leveling properties. During paving, each truck leaves the plant along a carefully planned route, heading toward a job site, where the construction crew has already prepared the base layer. Asphalt paving process. Now comes the most important stage in building a highway: laying the asphalt. In modern infrastructure projects across the United States, asphalt paving technology that incorporates rubber from recycled tires has advanced far beyond what it used to be. Dump trucks bring in hot asphalt kept at around 160 degrees Celsius and unload it directly into the paver's hopper. From there, the conveyor system and augers continuously move the material toward the back, making sure the mix is spread evenly across the full width of the road. The real magic happens at the screen, the vibrating tamping and pressing unit at the rear, which can achieve 85 to 92% compaction while the asphalt is still extremely hot. This allows the layer to be shaped, compressed, and smoothed in a single pass. This method is especially effective for the surface coarse or stone mastic asphalt, which is only about 2 to 3 centimeters thick and cools very quickly. Using traditional vibratory rollers on such a thin layer can cause cracks or ripples, but with the automatic screed-on modern pavers, the road surface stays perfectly smooth, well-textured, and uniform along the entire stretch. In the past, the process required multiple rollers, vibratory, static, and pneumatic to achieve the proper density. Today, high-end asphalt pavers handle more than half of the compaction work inside the machine itself. The Vogella pavers from the Virgin Group are especially well regarded for their precision, material efficiency, and their ability to reduce roller work by 70 to 80% compared to older methods. After paving, a light steel roller may make one final pass to finish the surface, though many projects skip this entirely because the mat already meets standards. Straight out of the machine, thanks to these new technologies, the process of laying rubber-modified asphalt made from recycled tires has become faster and more uniform, producing highways that are highly durable and capable of handling heavy traffic and continuous use for many years. In this modern process, a single machine handles both tasks at once. As it moves forward, the front nozzles spray a thin layer of bonding material, the tack coat, directly onto the old pavement using asphalt emulsion or liquid asphalt. This layer acts like a glue that helps the recycled mix bond tightly to the existing surface and prevents any slipping or separation under heavy traffic. Right behind the spray bar, the same machine immediately places the recycled asphalt mix onto the tack-coated surface without any waiting time. The paver then spreads the hot mix to the designed thickness while the screed vibrates and compacts it continuously, forming a smooth and uniform layer with the proper initial density in a single pass, completing the traffic support system. Once the asphalt has cooled and reached full stability, the next step is applying the road markings that guide traffic. First, the crew uses laser measuring tools or guide strings to determine the exact position of each line, lane dividers, stop lines, and directional markings. After the layout is confirmed, the specialized striping machine is brought in. It usually applies thermoplastic reflective paint, which is heated to around 180 to 200 degrees Celsius to ensure maximum adhesion to the asphalt surface. As the machine moves, its spray head creates lines with the precise thickness and width required for highway standards. While glass beads are dropped onto the fresh paint, these tiny beads reflect car headlights at night, significantly improving visibility and safety. After just a few minutes of cooling, the markings harden, bond firmly to the pavement, and the roadway is ready for traffic, completing the surface of the new highway. The final step before completing the highway is installing the concrete barriers. These barriers are usually precast in a factory before being brought to the construction site. At the factory, each barrier is poured into high-precision steel molds to ensure all dimensions and angles are perfectly consistent. After pouring, vibrating tables compact the concrete, creating a smooth surface and increasing strength. Once the concrete reaches full hardness, each barrier is removed from the mold, quality checked, and numbered in the order they will be installed. At the site, cranes or specialized forklifts place the concrete segments exactly where the plans specify. Workers then secure them together using steel pins or bonding adhesive, forming a continuous and stable barrier line. This precast installation method speeds up construction, reduces road closure time, and improves safety during highway maintenance. After the concrete barriers are installed, the engineering team conducts a final inspection of the entire highway. They check road smoothness, drainage, performance, surface traction, and the structural quality of every section. Each component is approved only when it fully meets all safety and technical standards, and only then is the highway allowed to open for use. Conclusion. And so what was once considered hazardous waste, old tires, have been crushed, recycled, and become part of modern transportation infrastructure. Beneath the glossy black asphalt that millions of cars roll over every day lies a story of engineering, the environment, and smart recycling thinking. The information I've compiled is from various sources. Please let me know if there are any errors. See you in the next videos.